the organizers, Olivier, and Benjamin for inviting me here. And I'm happy to represent our group led by Lloyd Hollenberg at the University of Melbourne. And I just highlighted here the people involved in the work I'm going to present. James Wood in the early days, my PhD student David Broadway, and postdocs Liam Hall for the theory, David Simpson for some experiments, and myself. So I'm going to talk about cross-relaxation with the NV center in diamonds. And I will show how we can use those effects for EPR spectroscopy, but also NMR, and more recently we show that we can hyperpolarize nuclear spins external to the diamond. So when you want to detect spins using the NV center in diamond, you have broadly two kind of approaches. The mainstream is what I call here active sensing, where you drive the NV spin transitions, say between the 0 and -1 spin states, in order to engineer the Hamiltonian and make it sensitive to specific transitions in your target spin system. So that's the mainstream, and the other approach that's been quite actively developed in the past few years is a sort of passive sensing, where you just monitor the evolution of the spin state of the NV center without actively driving it. So that's a kind of relaxometry detection technique, and to be frequency selective to your spin system, you can either drive the target, and we heard about that on Tuesday in the context of FMR, and also on this puzzling observation of P1 spectroscopy via driving this P1. And I also point to these papers that we published last year, where we also drive the P1s only, not the NV, and we see a response on the NVPL. But I'm not going to talk about that today. I will focus on cross-relaxation, where we don't drive neither the NV nor the target spin system, and we just use cross-relaxation effects to be to get a spectral information. So how does that work? So when you have two spin on resonance with each other, which is you match, say, the frequency here between the 0 and -1 of the NV with your target spin, so consider a spin half for now. So when you match those two frequencies and those two spins are coupled by some interaction, so say here it would be the magnetic dipole-dipole interaction, or the half-fine interaction for nuclear spins. If your NV starts in 0, then you will interact only with the target spin if it's in the up state, and they will start flip-flopping, so exchange energy coherently. And this is what you get if you watch the 0 state of the NV. You would get oscillations in black. So of course that's without dephasing. You have an oscillation rate of 2A, where A is a coupling strength. When you have dephasing, so you can have a damped oscillation, so the red curve, with the damping rate being given by gamma 2 and 2, where gamma 2 is the total dephasing rate of the system. And in the regime of strong dephasing, which is relevant for external spin detection in our case, you will have a simple exponential decay with a decay rate gamma 1 here given by A square on gamma 2, so it's proportional to the square of the interaction strength. Now, where can you see those resonances? So for electron spins, it's going to occur around 512 Gauss for a free electron, and that's because of the 2.87 gigahertz of the zero-phase splitting of the NV. And you would monitor that experimentally by measuring the relaxation rate gamma 1 or the spin lifetime T1 as a function of the strength of the magnetic field being applied along the NV axis. And the width of that resonance is simply gamma 2, the dephasing rate. So there is an angular dependence of the interaction, and that's shown here. The red line is a decay rate that you would measure on resonance as a function of the angle of your target spin relative to the quantization axis. And you see that it's maximally sensitive at 90-degree angle, and it's actually vanishingly sensitive on axis at 0 degree, which means you cannot, you don't interact with the spin that is along the NV axis. So a very basic experiment to illustrate the concept, done in a quite boring system, which is the P1 center in diamond. So we take a type 1b diamond and we look at a single NV center, and we have all those substitutional nitrogen impurities in the diamond, so-called P1 centers. And the experiment is done as follows. We don't measure the full T1 curve, we just pick a given tau time. So we initialize with a laser pulse, we wait for tau, and we read out. And this graph here shows the PL readout as a function of the magnetic field strength, or the equivalently the NV transition frequency. And we obtain this characteristic P1 spectrum that comes from the Hyperpolarisation interaction with the nuclear spin of the NAT chain. So a bit more interesting, if we take a pure diamond, so a CVD diamond that is free of P1s, and if we take a near surface NV, so say about 10 nanometers from the surface, we get this kind of spectrum where now we have only one line, which is at the G equal 2 line, so unpaired electrons that come either from they come from the surface, from dangling bonds or some kind of surface state. Yep. You could extract that. We haven't done that for that particular sample. So P1, you would see the Hyperpolarisation structure, but it could be internal defects, for instance, dye vacancies or this kind of defects, so other defects inside the diamond. Yeah, so in that experiment, there's nothing we can say, just it looks like unpaired electrons. That's all we can say. So actually that's related. We used that technique of EPR spectroscopy to look at a different situation where now we implant high density NV centers via night chain implantation. And here we have, so we create a lot of damage during this implantation, and the idea is to try to characterize the paramagnetic environment of the NV centers. And in that experiment here, so we measure the relaxation rate here, so from the full T1 curve, again as a function of the frequency relative to the free electron. So we have this G equal 2 line at the center, and we see that we have satellite peaks that are very far, like it's 200 megahertz, 400 megahertz plus. So it's not P1. P1 would be inside that central peak here, and we actually assign from looking at the literature, we assign those to the dye vacancy defect. And what was interesting is that we found that by annealing again the same diamond at a higher temperature, so here 1100 degrees, we reduce a lot the content of in paramagnetic impurities around the NV centers, and essentially we suppress completely the dye vacancy, and it's consistent with previous studies that showed that higher temperature annealing anneal out some of the dye vacancy, also form larger clusters. So you still have a lot of paramagnetic content, but they form larger clusters, multi-vacancy chains, even rings of vacancies, and those shows up in EPR as just unpaired electrons. So that's what we see here. Of those, so that's an interesting point. So yeah, it's pretty much 100 megahertz here, and that's that means those paramagnetic species are very short-lived, so 10 nanoseconds. And that's consistent with what you see also in EPR line width for this kind of sample. So yeah, that shows that unlike the P1, which is very narrow, in those kind of samples, the P1 you don't even see it because all the spins that we detect here are very short-lived. And that's actually quite important, I think, to illustrate that the technique is good at actually detecting those short-lived species, as opposed to, for instance, DEER, double electron-electron resonance spectroscopy, which is not very good, where you use the NV, which is not very good at looking at very short lived species, because then you lose in sensitivity. Your phononic decay, no. So here, the cause for this short T1, yeah, might be phononic related, yeah, sure. But you don't see that in very deep NVs in type 1b, for instance. It's all very narrow, and here it's very, yeah, it's very broad, and it could be also related to the surface. Yeah, possibly. So I think that's actually a good illustration of how useful this technique is for this particular situation where you have very short-lived species. And in that study, we correlated then the paramagnetic environment, so the noise spectrum, with other properties of the NV centers, which are interesting for sensing. And for instance, the same sample here, we found that we can decrease the line width in ODMR and increase the anecho T2 time by a factor 2. Yep. It's still, no, not the P1, it's still limited by damage. So by this G equal 2 peak, which is not P1, so it's much, so dye vacancies and other vacancy related impurities. So it's actually even shorter if you take a naive model. So it's actually a complex physics of the interaction with all P1 and all those vacancies that detune each P1 essentially. So they don't interact that much as much because you have the dynamic list. So you would expect actually longer if it was just P1. But yeah, it's work in progress to actually model that completely. So we think we are anyway limited by all impurities, vacancies, vacancy chains, and also P1s, and altogether those limit the T2. P1 density, so we implant here 10 to the 13 per centimeter square at 14 keV in that particular sample. All right. So that's so that's to illustrate that we can do EPR spectroscopy, and you can. It's a trivial extension then to do EPR microscopy or imaging. For that, you need just an NV ensemble and just image the PL on a camera. This way you can, on each pixel of the camera, get an EPR spectrum. And with our colleagues in our group have shown that, I've illustrated that with copper ions in solution. So you put a solution of hexaqua copper onto the diamond, and you see here the spectrum. So in green is a reference spectrum with no solution, and in blue you have this shoulder here, which comes from the copper ions, and it's known that copper have a different G factor of 2.2, which is what we see here, and we can extract that from Felix the data. And if you want to show imaging, so we've done a very basic proof of principle of that by just making a PMMM mask to protect the diamond, except in that region here, where the NV sees the copper ions, and that's what we see here in bright signal, which means a smaller T1. So I've talked about EPR. So one question we asked ourselves a couple of years ago was, can we use the same concept to do NMR? So there are a few complications in doing that. So one, of course, is that the germanium ratio is much smaller for nuclear spin, which means weaker interaction. And the other one is that the resonances are going to occur near the ground state level anti-crossing, so at 1024 Gauss, which brings some complications. So you expect two resonances now instead of just one for electrons, one before and one after the G-slack. And those two resonances have different angular dependencies. And that's because, well, the half-fine interaction terms are different, and it can be seen by seeing that here the NV is going to give energy to the target or take energy in the other case. And we have different terms. And I show here in solid line the angular dependence for the after G-slack resonance, which is the same as the electron spin case, and in dashed line the before G-slack case. And you see that this one is weaker, and it's maximally sensitive on axis at 0 degree, and importantly, it's actually vanishing at 55 degree, which is important for external sensing with a 1 over surface. So this is a G-slack structure, which comes from so anti-crossing from the half-fine interaction from the NV electron spin with the nitrogen nuclear spin of the NV. And you have the two cases, the two isotopes for nitrogen and 14 and 15. And this is the structure we get in the two cases. And we see that it's actually, there is no universal good isotope to use here. If you look at where you expect resonances with hydrogen, so proton spins at 4.4 megahertz at this field, you only have one resonance after the G-slack 4 and 14. And if you want to detect carbon-13, which is at 1.1 megahertz Larmor frequency, you can only use the N14 because there is a vanishing transition probability at this frequency with N15. So we tested that NMR ID initially looking at proton spins in immersion oil prepared on the diamonds. We have about 10 nanometer deep NV here, and this is the ODMR spectrum again as a function of field. And then we zoom in around where we expect the resonance with protons, so 4.4 megahertz, and we take a T1 measurement, so again with a single tau here of 200 microseconds, and we detect a resonance at the expected Larmor frequency, so here it's normalized, but at 4.4 megahertz, which we attribute to the proton spins outside or on the surface of the diamond. And this is a full T1 curve when we sit on resonance in blue, which has a shorter decay than the off resonance T1 measurement. You can do the same with an N15. So here you expect two resonances now, one before and one after the G-slack. And that's what we see here. And actually, so this is with 20 microseconds evolution time, where we mostly detect the one after the G-slack, the zoom in here, and the other one we have to extend the interaction time up to 100 microseconds here to see it, and that's because of the angular dependence that I mentioned before, where the before G-slack is usually weaker on average than after, and you've got this spin mixing feature here, which is quite well understood. All right, so just a technical side note to say that we now use temperature control of the magnet to do the scanning of the magnetic field. So that's a trick which is known in the community, that there is a temperature sensitivity of the magnet, and it's usually annoying when you want to stabilize the magnetic field. And here we use that as a resource to scan the magnetic field. So it's very simple. It's roughly linear, the temperature dependence at room temperature. So if you just scan the temperature, for instance, here by 4 degrees, you shift here the frequency of the NV by up to 10 megahertz. That's near the G-slack. And you could imagine having an even wider scanning range. And that's sufficient for most NMR and NPR spectroscopy that you can do with cross-relaxation. And the other application of that, of having this temperature control, is that you can stabilize the magnetic field, which usually fluctuates due to room temperature fluctuations. As we heard from Gregory a few days ago, that usually even a quarter of a degree give rise to significant fluctuations. For instance, here we have 2 megahertz peak-to-peak fluctuations in the NV frequency over the course of several hours. And we reduce that by an order of magnitude just by controlling the temperature with specific feedback mechanism. All right, so that brings me to the last part of my talk, and actually for that one, it's quite important to have a stable magnetic field because you need to be on resonance, so being at this cross-relaxation resonance for a long period of time, and you cannot just correct for drift. You need to be just on resonance, otherwise decreasing the efficiency of the process. So the idea of hyperpolarization here is very simple. So it's an example of DMP where we use the polarization of the electron spin, here the NV that we polarize optically, to transfer that to nuclear spins. And the way we transfer that polarization is by using, again, those cross-relaxation resonance. So again, we have our NV on resonance with a nuclear spin. If we initialize the NV in 0, it will interact with the target spin only if it's in the up state. If the target is in the down, there's no interaction. And in that case, they will flip-flop. And if you wait just long enough to have one flip-flop, then you flip your spin. So you flip your target, and if now you reinitialize your NV, this spin that flipped doesn't interact with the NV, and now you're going to interact with another one. So you can flip that way, so it's pictorial, of course, but you can flip that way more and more spin as you repeat that process. And that's how you can end up with a large number of polarized spins by keep repeating that simple sequence, which is initialize, wait, and repeat. You can also initialize the NV in the opposite state, in the -1 state, by simply adding a pi pulse to your sequence. And in that case, you're just going to initialize in the opposite state, so the up state, say, here. And if you alternate those two sequences, that we call creep and I-creep in that presentation, so creep for cross-relaxation induced polarization and inverse creep. If you alternate those two, then you just prevent polarization buildup because you're going to polarize one way or the other alternatively. And that's going to be our control sequence. So we tested that idea initially on carbon-13 inside the diamonds. So we have a deep single NV in a 1.1%, so natural isotope concentration. And as I mentioned before, you have two resonances with carbon-13 if you use an N14 NV. And so the difference between those two, beside the different angular dependence, is that you will polarize the spin in opposite states. In one case, you will polarize, say, up here and down here if you initialize NV in 0. So we have different end states for the bath. So this is the experiment where we sit, for that graph here, we sit on the resonance after the G-slack. So we have the NV at 1.1 megahertz. And we do the following measurements. We measure the PL as a function of the tau time here with two different sequences. In orange, it's when you alternate creep and I-creep, where in that case you expect to prevent polarization buildup. And we see fast oscillations that correspond to the flip-flop between your NV and your bath of carbon-13 spins. Now in gray, it's when you use a polarizing sequence. So you just initialize weight, and I just added here another part of the sequence to normalize the signal, but it doesn't change the evolution. We just apply pi poles just before readout. So it doesn't change anything, just a way to normalize your signal. And this way you have the two curves here, which are flat. And they are flat simply because there is no interaction with the carbon-13 because they are polarized. They are in the non-interacting state. And you can see that in the frequency domain as well. If now you pick a tau time and you use those two sequences while varying the magnetic field, then you obtain those two spectrums. So in orange, it's when you use the alternating sequence, so you prevent polarization buildup, hence you see this interaction with the carbon-13 once before, once after the G-slack at the expected frequency of 1.1 megahertz. And in blue, it's when you use a polarizing sequence, or CRIP, where now, while you scan, you polarize, you keep polarizing your bath when you approach the resonance. Hence, you see a suppressed interaction. You don't see the carbon-13 simply because they are polarized, hence in the non-interacting state. And if you see it on the, so that was after the G-slack. If you see it now before the G-slack, you can repeat the time resolved experiment, and that's what you get. So you get again an oscillation only when you use the alternating sequence. And we have a slower oscillation, and that's because the oscillation frequency is given by the sum of the Hyperpolarisation coupling to each spin of the path. And because of the different angular dependence, you get a different frequency. And as I said, we expect a slower coupling in general before the G-stack. So you can also watch the polarization buildup. So you, for that, you vary the number of polarization cycles. So for instance, you apply n times I creep to polarize one way, and n times creep to polarize the other way. And if you increase here, for instance, n from 1 to 3, and do the time resolved measurements, you see that you have a decrease of contrast with the same oscillation frequency up to the point where the signal will be flat, no more interaction. And that behavior is in agreement with our theory. Yeah, that's right. So you have a damped oscillation, but we are in a strong regime where we see still some oscillations. Yeah. And here it's when you apply. So you pick a tau here, and you vary n. So you have 30 cycles of I creep and 30 cycles of creep, and you see a rapid saturation of the polarization. So of course this is with a short tau of a few microseconds, which means in that experiment, in fact, we only probe the nearest spins. There is not enough time to interact with the most remote spins. So that means even though we might transfer polarization beyond that because of spin diffusion, here we are not able to monitor that. So if you want to probe further, you need to increase tau. And that's what we've done here in that graph, where we in fact take a full T1 curve by scanning tau from 0 to 10 milliseconds while applying this polarizing sequence or the alternating sequence in orange. And you see, in fact, so that's the extension of the flat gray curve that I've shown before. If you probe further, then you see a decay, but this decay is actually matching the phonon limited decay that you would measure off resonance, which means, so that's the blue data here, which means at this stage of the experiment, which is, you measure that over hours, at this stage of the experiment, all the carbon-13 that are in the sensing volume of the NV are polarized. So as far as the NV can tell, there is no more non-polarized carbon-13, hence no more interaction. So that still doesn't mean you don't polarize beyond that, because again, you have spin diffusion, so you polarize probably further than this sensing volume, which is a few nanometers, but you cannot probe that with the NV itself. So to actually get an estimate of that, how far we polarize, we developed a model, so Liam Hall developed this model where you have, so it's a continuum description of the polarization at a given point in space. You have dipole-mediated diffusion, you have Hyperpolarisation mediated cooling, which is our cross-relaxation effect from the NV, and also spin lattice relaxation, which will limit the extent of that volume. And the simulation shows that after I think 5 hours of polarization, which is as in experiments, we get a fully polarized path within 20 nanometers of the NV. Yep, that's right. All right, and so the one goal was to polarize external spins outside the diamond, because that's important for applications. And so we've tested that by looking at protons in PMMA prepared on the diamond, so about 10 nanometer deep NV again. And this is the data where we have again the spectral observation of that with the alternating sequence here in orange. which shows a resonance with the proton spins, and the interaction is suppressed. It's noisy, but it looks suppressed in blue when we polarize. And if you sit on resonance and take a full T1 curve, you get in orange when you have the full interaction, when you depolarize, and in blue when you keep polarizing. And we see that, so there is an increase in T1, but it still doesn't quite match the green here, which is the off-resonance T1 that we measure, which means within the sensing volume, there is still some non-polarized proton spins. And that's limited, of course, by their intrinsic T1, which limits the extent of polarization that we can achieve. And if you simulate that, which reproduce actually those T1 change that we see with the condition of the experiment, we find that we have about 10 to the 6 spins that are polarized at 50% level, and that corresponds to a volume of 20 nanometer cube. So I'll just finish with a comparison with Harmathand polarization, which is the other approach that is more often used actually in the NV community to polarize spins to transfer polarization from the NV to nuclear spins. So Harmathand is actually also a cross-relaxation effect, but in the rotating frame, you drive the NV in such a way that the radio frequency of the driven system matches your nuclear spin, and you can then transfer polarization in the same way, and you can choose which way you polarize your target by changing the axis, for instance, of this continuous driving. And so the question is what's different between those two, and one difference is the angular dependence of the interaction, of the flip-flop interaction in the lab frame versus in the rotating frame. And so those equations are derived here. This is a flip-flop rate if you have just one target spin with no dephasing as a function of the angle here. So it's plotted as a function of the angle as shown before of the NV relative to the quantization axis. And we find that Harmathand, which is in blue here, is always lower than one of the two cross-relaxation, lab frame cross-relaxation. And of course, the after G-slack is the strongest. And by some factor, which is factor 2, 3 here. But remember, in the strong dephasing case, the interaction strength is actually the square of that. And here we show, so yeah, the cooling rate is A squared on 2 gamma 2. We have the same gamma 2 in the two processes. And this graph shows here the polarization rate, effective polarization rate of an ensemble of spins, so semi-infinite volume of target spins here, as a function of the angle of the NV relative to the surface. So 0 degree is perpendicular to the surface, 90 degree parallel. And we find that cross-relaxation in blue here after G-slack is always stronger than Harmathand in green. And there is actually a large difference, even if you compare the optimal case, 0 degree for Harmathand here and 90 degree, you have a factor 8 pretty much between the two, which is significant. And to verify that this translates indeed into an increased number of polarized spins, we simulated that situation where you have an NV semi-infinite volume, and this shows the total polarization, so the total number of spins that are polarized as a function of the total time using the optimal tau that you can use for each technique, and using the optimal angle. And you see that cross-relaxation after G-slack at 90 degree angle gives you a saturated number of spins. So the saturation comes from the T1 of those target spin, which is 1 second in that simulation. It's 8 times larger again than the saturated value that you get for Harmathand. So this suggests that if you neglect all the other differences, the differences on flexibility versus detuning and so on, just the raw efficiency of the technique seems to be a factor 8 difference in favor of the cross-relaxation after G-slack. And we've done an experimental verification of that to some extent, so using carbon-13 inside a diamond. And that shows for the same NV, we looked at this flip-flop oscillation for, so in the circle here for cross-relaxation after G-slack and Harmathand in triangles, which is clearly slower, so flip-flop rate is slower. And we've reproduced that on several NVs, and that plot actually shows the flip-flop rate of one technique versus the other, and it's always on the faster side here, and it's as expected from the theory, just from that different angular dependence. And we also looked at the polarization buildup of the two techniques, again for 5 different NVs, and just notice the different time scale here, and it's always, for the 5 NVs we looked at, it's always quicker with cross-relaxation than with Harmathand. So we think it's a strong suggestion that there is clearly an intrinsic difference in efficiency between the two techniques. Then you have to consider all the other things, the flexibility of the technique. Of course, here you have to be well aligned, precisely aligned. You cannot afford to have any misalignment and so forth. So other things to consider then, apart from that efficiency. Yeah, so that's a point that is very interesting. We haven't found in our modeling of Harmathand any difference. Like if you consider quasi-static dephasing, you get the same equation, which is this A square on gamma 2 with the same gamma 2. There is no decoupling effect in the cooling rate. So that's what we found. And it's not clear actually why there is no decoupling effect in that regime where you want to transfer polarization. So that's something I would like to discuss with you possibly to understand that. So that brings me to my summary slide. So I showed how we can use cross-relaxation for APR. And I think it's actually interesting in the context of looking at short-lived species as opposed to DS spectroscopy. For NMR, it works. So a big drawback here that I didn't discuss, but it's the spectral resolution, which is limited by T2 star, the dephasing rate. So it's very bad compared to what we can do now with dynamical decoupling. But more interestingly, the hyperpolarization of nuclear spin with the same technique, I think, is promising because it looks like it's more efficient than Harmathand. And with that, that's my thank you slide. Thank you.